Hey, good morning, everybody. My name is Ben Crawford. I'm going to tell you guys this morning about our low-cost air quality sensor network that we had set up in Hawaii during the 2018 Kilauea eruption. First, I'd like to acknowledge my co-authors, Jesse Kroll, David Hagen, and Colette Held, all from MIT. So first, a little bit of background about VOG, or volcanic smog, and it's how it's really an ideal system for what we are trying to accomplish. So there's one major point source of SO2, sulfur dioxide, coming out of the ground and being emitted into a really clean, pristine background environment. The chemistry then for this CO2 is fairly straightforward. It undergoes some photochemical oxidation, and over a time scale of a few hours, transforms into fine particulate matter, mostly sulfuric acid. So the meteorology on the Big Island where we were is very steady, nearly constant trade winds out of the east, northeast. So that makes the plume travel in a very predictable direction most times. And finally, there's a lot of local community awareness and engagement. Fog is a big environmental issue on the island, so it made it easy to approach people, talk to people about this, and eventually set up our monitors. So the original objectives of this work were to build and set up a network of sensors measuring SO2 and particulate matter around the island, and to use this as a community resource, make the data available, use this as an educational tool for K-12 teachers and students, and also as a research test bed. So these original objectives, they changed somewhat once the volcano started erupting in summer 2018. I'll tell you guys that story coming up in a few slides. But first, a little bit more background about the Big Island. You can see here it's about 10,400 square kilometers and nearly 190,000 residents. We're looking at these steady east-northeast trade winds that are blowing nearly constantly. It's pretty steady. So the main population centers here are Hilo on the east side. It's the biggest city on the island, about 43,000 people, and then Kailua Kona is the main settlement on the west side, about 12,000 people. But this whole coast is pretty populated on the west side. So here's the volcanoes, the volcanic vents. These two craters have been erupting fairly constantly. Halemaumau since 1983 in an ongoing effusive eruption, and then from 2014 to 18, both these locations were pumping out CO2 about 5,000 tons of SO2 per day. So this made it the largest single source of SO2 in the US. And here's where the 2018 Lower East Rift Zone eruption occurred. So once these volcanic emissions are in the atmosphere, they get picked up by these winds, and the plume gets carried down towards the southwest. And this part of the coast, this part of the island, is primarily affected by SO2, and it's fairly sparsely populated. But as this plume travels in the wind, it gets caught up in this lee side eddy on downwind side of the island where wind speeds are slower, this big purple area. It's had time to transform into particulate matter. So this area of the island is more heavily populated and people are exposed to this sulfuric acid particulate matter. And these two things together, SO2 and PM, are what's known as VOG, or volcanic smog. So there is a network of regulatory air quality monitors that had been set up, 6 stations, 3 downwind and 3 upwind. There's also a couple of monitors in the national park used for volcanic monitoring. But as you can see, they're fairly sparsely laid out on the island. So what we had planned, so this is during 2018, what we had planned was for me in January, for us as a group to go to the island, and we actually did this, hold some teacher workshops, public presentations, health clinic meetings, really to lay the groundwork for us to go down and set up our network. Then over the spring and summer, start to design and build things. The plan was for me to move in August, move to Hawaii, start some teacher training workshops, and then really deploy the network starting in fall. But all of this timeline kind of got blown up when this started happening. Okay, so I took this video in early May after the eruption had started. You can see there's massive amount of lava happening in a residential area. So these fissures that were opening up in a populated area and really pumping out a lot of lava, as well as tremendous amount of sulfur dioxide. So that lava you were seeing in the video is feeding this lava river and flowing down to the ocean. And eventually it covered an area of over 35 square kilometers, destroyed hundreds of homes, displaced thousands of people. And so you can see on this, there's this line of vents and fissures that opened up, kind of unzipped along here. And this was really pumping out a lot of SO2, okay? Over 50,000 tons of SO2 per day. So we've increased an order of magnitude from what was happening before. You can really see the trade winds, the steady winds pushing all these plumes in a constant direction. Here's another photo that illustrates that. We have this lava river bisecting the photo here. And on the upwind side, things are really nice and green and lush. And on the downwind side, really have been chemically burned from these really high SO2 concentrations. So we have this tremendous amount of SO2 happening, emissions happening in a pretty populated area. And so we could see this actually from space. Right? So on the top here is SO2, and on the bottom is a aerosol optical depth. And so we can see the plume extends for really far distance. We're looking at aerosol optical depth from the satellite. So we could see this from space. We could also measure this on the ground. So this is a graph from one of the air quality regulatory stations in Ocean View, downwind of the eruption. This is the entire year of 2018, SO2 on the top, PM on the bottom. And you can see this really distinct increase during the eruption in early May in this gray shaded area, and then it subsides at the end of July, early August. And so we see this real tremendous step change in emissions and air quality. But as we said before, these stations are pretty sparse around the island. There was no actual monitoring near the eruption. There was a station, but it got destroyed by lava within a few days. And then the average resident lived nearly 18 kilometers from a station. So we received some calls from our community partners to put out some more air quality sensors. People were really concerned. So all of a sudden our mission has really now changed to this emergency response, okay, because people were really concerned about these high levels of SO2 and PM. So we sent 10 existing monitors to the Hawaii Department of Health, and these were deployed really in the immediate vicinity of the eruption. In the meantime, we built 30 new sensor boxes to measure SO2, particulate matter, and also H2S. And we calibrated these in the field against DOH stations, and these were deployed around the island, mostly at K-12 schools. We also set up a website for real-time data access so people could monitor conditions in near real time. Here's a quick overview of our sensors. We were measuring SO2 and H2S using electrochemical sensors by AlphaSense, and then AlphaSense's optical particle counter, OPC, as well. Measured ambient relative humidity and air temperature, and the whole thing was powered by rechargeable solar panels and batteries. So we logged the data and transmitted it by 3G cellular signal to an online cloud database using a microcontroller, and the whole thing cost about $1,000. So this is what we measured when we put up all our sensors. So this is a 2-week period at the end of July, and this is showing average concentrations. These are graduated symbols, so bigger circles mean higher concentrations. On the left is sulfur dioxide, and on the right is particulate matter. So we can see highest concentrations of SO2 are just downwind of the volcanic vents on that southwest coast. Now for PM, the highest concentrations are on that Kona coast, the west side. So things have had time, the plume has had time to transform it into this fine particulate matter. So this is great. This is what we'd expect to see, but we have a lot more sensors on the ground now. We've been able to put up sensors in areas that didn't have monitoring previously. So we can see some areas that were affected by particulate matter further up the northwest coast there that normally don't see particulate matter and normally aren't even monitored. So this is great. With this extra density of stations, we can get a better idea of the spatial distribution of this fog. And we can also get a better sense of the population exposure as well. Okay, so here along the x-axis for both of these, we have population. On the left is SO2 and on the right is PM 2.5. So each one of these bars represents a different station. Now the width of the bar is scaled according to the population that lives within 5 kilometers of this station. So wider bar means more people live by that station. And the height of the bar is the average concentration during that 2-week period. So what we just saw on that map. So this is the average population exposure during this time period. So with this, we can get a better idea of how many people and where were exposed to which of these different air pollutants. So this is looking at the mean exposure. We can also look at a distribution. Okay, so now we have concentration along the x-axis, and this is and on the y-axis is hourly exposure frequency of SO2 on the left and PM 2.5 on the right. Okay, so each one of these colored bands is a station, and it's been scaled according to its population. So a wider bar means it has a more heavily populated area. So this gives us an even more detailed view of how many people were exposed to what different levels of concentration during this period of the eruption. So this is really cool. We're able to see a much higher resolution estimate of population exposure than we were able to before with just a regulatory network, because we have this high density of stations. So with all these stations, we're also able to map out the pollutant transformation. Okay, so as this plume changes, it's moving over populated areas, so people are being exposed to different populations. And now with all these extra sensors, we're able to really track that transformation. So what we're looking at here is downwind distance from the vents, and then the ratio of SO2 to PM 2.5. So we can see this real nice exponential decay. So as we're getting further away, we're reducing the SO2 and it's being changed into PM 2.5. So based on this, we can estimate a time scale of this reaction rate and come up with a mean oxidative lifetime of SO2 of about 15 hours. So this is a new method, a new way to look at this kind of transformation with lots of different stations. We can get an average of this over a long period of time instead of just a snapshot like it's traditionally been done. Okay, so this brings us to the end of the eruption, and in early August, we can see SO2 really drops off and PM takes a few more days to clear out. So this is now the cleanest air on the island since 1983, and a really unique opportunity to measure baseline conditions. And this is right when I moved there too. So I moved there with this really nice network and get to measure some really clean air. So finally, to wrap things up, we're still measuring, we're still holding educational programs. Now we're also including low-cost weather sensors. And we found that these sensors are really well suited for the kind of emergency monitoring situation that we found ourselves in. But we need a lot more at communication, so this can really coordinate and fit with government agencies and emergency management protocols. So also the ideal data presentation and format can really vary dramatically depending on the target audience. And then finally, these kind of dense networks really provide valuable high resolution observations of population exposure and pollutant transformation. Okay, finally, I'd like to acknowledge all the people who made this possible, including the many teachers and sensor hosts on the Big Island. Thank you.